Narsareddy Tummoru, sir, to speak few words on this occasion.
Yeah. So good morning, everybody. So especially Murali Krishna Garu and Dr. Varma Garu and coordinators of the workshop, Dr. Ahmad and Dr. Veranna Garu. And also participants from various institutes across the India. So good morning, one and all. Today, workshop is mainly on emerging technologies in EVs as well as hydrogen technology. So I think you might have already known, Government of India is setting up many of the research programs on Maha EV as well as some of the other Maha programs on hydrogen systems. As a part of this Maha EV, I think Government of India coming up with setting up of around 7 e-nodes across the country, and maybe that are led by prominent institutes like IITs, IIT Mumbai, IIT Kharagpur, IISc Bangalore, and so on. And now currently that phase is going on. So in the upcoming years, maybe a lot of funding they are expecting for they're expecting to make in the EV sector. Surely there is a very huge growth in the electrical vehicle market. So maybe last month we attended one meeting at ANRF at IIT Delhi, which is conducted by these ANRF people, and there is much more expectations from the researchers across the India, and also development of manpower in the area of EVs and so on. I think you might have already known there are various subsystems in the EVs, right from the beginning of energy storage systems to the drivetrains, EV charging infrastructure, and so on. Maybe I will concentrate all these points in my talk. So now just I am setting up a tone for this workshop, and maybe I also wish this workshop, 6 days workshop, would be a big success at the end of the 6 days. So maybe we will discuss much more details in my session. So with that, I am stopping here. Thank you, one and all.
Thank you, sir, and accepting our invitation and sharing your thoughts. Now, learning never stops because knowledge has no limits. Once again, I extend a warm welcome to everyone. Thank you. We sincerely hope that this program will be gain success and become another memorable event of Sagi Ramakrishnam Raju Engineering College. I would like to request co-coordinator Dr. Veranna sir to propose vote of thanks of inaugural.
So good morning one and all. I am Dr. Veranna, Associate Professor and Co-Coordinator of the AICTE ATAL Faculty Development Program. It is my privilege to propose the vote of thanks for this inaugural ceremony of the FDP on the sustainable energy solutions and emerging technologies in electrical vehicles and hydrogen storage. So first I sincerely thank the AICTE Training and Learning Academy for sponsoring this prestigious 6-day program and providing a valuable platform for the knowledge sharing and professional development. I express my heartfelt gratitude to the management of Sagi Ramakrishnam Raju Engineering College, especially our Secretary and Correspondent Sri SRK Nishant Varma Garu, Director Dr. M. Jagpati Raju Garu, Principal Dr. K.V. Murali Krishna Raju Garu, and Chief Administrative Officer Sri Dilip Chakravarti Garu for their continuous encouragement and support. I sincerely thank our Head of the Department, Dr. B.R.K. Varma sir, for his guidance and motivation, and our co-coordinator, Dr. Azhar sir, for his excellence planning and coordination. My specially thanks to all the organizing committee members, faculty, staff, students, media, transport, hospitality, and housekeeping teams for their dedicated efforts in making this program successful. We are grateful to our distinguished resource persons from IITs NITs, and leading industries for sharing their valuable knowledge and expertise. I also thank Radhan Technologies Private Limited for facilitating the industrial visit and providing practical exposure to EV and battery technologies. Finally, I sincerely thank all the faculty members, research scholars, industry professionals, and participants from various institutions for their enthusiastic participation. With this all, once again, thank you all the dignitaries, resource persons, participants, and everyone associated with this program. I wish all the participants an highly informative, interactive, and rewarding faculty development program. Thank you, one and all. Jai Hind.
Okay, let's have a tea break at this moment. I request you to all the participants, the back session will start in 10 minutes, 15 minutes.
ఫుల్ స్క్రీన్ చేయాలి ఇదేంటి క్లిక్ అవట్లేదు అది ముందు హైడ్ చేస్తాను అది మార్చడానికి రావట్లేదు స్టూడియో ఒకసారి ఇప్పుడు ఎంత 1,20,000 1,50,000 ఇప్పుడు నేను కొన్నప్పుడు 1,20,000 నాకు 90 పడింది ఏదో ఒక సేల్ ఏదో డాడీ కరెక్ట్గా సేల్ ఏదో ఉందంటే ఇది ఐఫోన్ 17 అది నాకు 12,000 ఆఫర్ అంత పడింది 12,000 తగ్గింది ఇప్పుడేమో ర్యామ్లు ఇవన్నీ కూడా రేట్లు తెచ్చేసి నీకు యాప్స్ డౌన్లోడ్ చేసుకోవడం ఉండదు సిస్టమ్ అంతా వేరే కానీ ఇందులో విండోస్ ప్యారలల్ అనేది సాఫ్ట్వేర్ ఉంది అంత ఎక్కువగా ఉంటే కాకపోతే సంవత్సరానికి 7,000 అప్పుడు దాని కూడా ల్యాప్టాప్ కొనుక్కోవాలి ఆ డబ్బులతో కానీ విండోస్ రేంజ్ దగ్గర ఏం కాదు 90,000లో విండోస్ తీసుకో 70 ఉంది కదా థింక్ నాకు రాసి నువ్వేం చేయడం సాఫ్ట్వేర్ అంటే స్ట్రెచ్
పైన పైన పెట్టుకో పైన పెట్టుకో
ఏదైనా అసలు తిరగట్లేదు
సరే ఇంకా దాని మెజర్మెంట్స్ అంతే అనుకుంటా.
మామూలుగా స్ట్రెచ్ చేస్తే అయిపోద్ది కదా అని.
పైన అన్నీ అవుతున్నాయి.
చాలా స్క్రీన్ మీద ఏముందో కనబట్లేదు.
అంతే
స్క్రీన్ మీద కనబట్లేదు. బ్రైట్నెస్ తగ్గించిన పండుగ
అలా అన్నాను కదా ఫేస్ వద్దా అది చెప్పేది ఎక్కువ ఉంటుంది. పోస్టర్ మీదే ఉండదు. పోస్టర్ మీద ఏం కాదు కదా. కదా అది అది తెలియదు మనకి. ట్రాన్సిషన్ అవసరం ఆ స్క్రీన్ కొట్టినా వచ్చేస్తుంది, ఎందుకంటే ఇది అడ్డు ఉంది కదా. మాస్టర్ అడ్డు ఉన్న వల్ల మనకి తెలియట్లేదు అన్నాను. తర్వాత ట్రాన్సిషన్ కొట్టే సరిపోతుంది. లైట్లో ఆన్ చేయలేదు ఇంకా ఆపేతారు అంతేనా? అంతే.
చెప్తారు.
Shortly we are going to have the first session. Before the session begins, I would like to just extend a warm welcome to you all once again. I wish this FDP becomes an interactive. Let us not make it a one-way session. It would be very, very useful and effective if participants interact with the experts presenting their talks. So, keeping that in mind, I request all the external participants to introduce themselves before the beginning of the first talk. Just we want to know where from your name, your institution. That's enough. Okay. So please, all the external participants, please introduce yourself to the guests and other faculty members.
This is Dr. Satyanarayana from Swarnamala College of Engineering and Technology.
Please get seated.
I am Jay Bodley from Swarnamala College of Engineering and Technology. This is Bhimavaram from Sri Learning Program, Deputy Department.
My name is AICTE Attal from Mechanical Aditya. I'm from JNPT, Academic Department.
Myself, Ajay Kumar, English Department.
I am Present Jain, Assistant Professor, FDP Department, Vidyajyoti Institute of Technology, Hyderabad.
I'm Jiva from Andhra College of Engineering and Technology from FDP Department.
I am Bhimavaram from FDP Department, SPC Learning. Thank you.
Dr. Shiva, FDP Department from Inaugural.
FDP Application No from Engineering College.
Myself, I am from the Department of Mechanical Engineering. I came to discover this technology to enhance our automotive sector.
My name is Jay from SRKREC College of Engineering. Myself, Sunil Kumar, SRKREC College of Engineering.
Thank you all. It's interesting to see many faculty members from mechanical engineering department. EV is a multidisciplinary area, so hydrogen storage also. It's good to have people from different departments. Definitely, interaction you have will become very, very good. So without wasting time, let us quickly begin the first session. Thank you.
Once again, a very good morning to everyone here. It gives me immense pleasure to introduce our distinguished speaker for the morning session. Dr. Nasaretti Tumuru is an associate professor, Department of Triple at IIT Bhubaneswar. He obtained his PhD in electrical engineering from IIT Madras and his MTech in power electronics, electrical mission and drives from IIT Delhi. He has also undertaken postdoctoral research at Nanyang Technological University, Singapore, and a JSPS fellowship at Nagoya Institute of Technology, Japan. Dr. Tumuru has received several prestigious recognitions, including the Kesavaranganath Excellence Research Award, Osaka Award, Distinguished New Faculty Award, JSPS Fellowship, and Best IEEE Transaction Paper Award. He has successfully undertaken and contributed to several sponsored research projects supported by organizations such as CERN, DST, MHRD, Imprint2, and FinCoast, particularly in the areas of green transportation, intelligent microgrids, hybrid energy storage, wireless power transfer, and renewable energy based systems. We are delighted to have Dr. Nasaretti Tumuru with us and warmly welcome him to this faculty development program. I am confident that this session will be highly informative and engaging for all the participants. Over to the students.
Yeah.
to 8 faculty I saw actually. So there is a heterogeneous group here, electrical engineering and mechanical engineering. So but anyhow, so I will try to see how I can accommodate the mechanical engineering faculty also. But most of my talk, if you see, it is related to the electrical side, and I request mechanical engineering colleagues to bear with me, and also to try to interact with me when the talk is going on. Yeah. So today, yeah. So today, so I would like to discuss most of the concepts on this electrical vehicle charging infrastructure. So this is one of the very important vertical in the EV ecosystem. Okay. So if you see the current scenario, especially deployment of electrical vehicle, one of the bottleneck in the country, if you look at charging infrastructure. Okay. So some of the trends in the electrical vehicle charging infrastructure and all, I would like to discuss today in a generic way, and also some of the outcomes that we carried out as a part of some of the ANRF projects that are funded by our central government, the IIT Bhubaneswar. That also I would like to discuss. So these are the works carried out by our PhD students at IITs. So maybe I have few students at IIT Mandi and few other at IIT Bhubaneswar. So the PhD students work only I am presenting today. So if you have any doubts in between, you try to raise the questions. So we'll interact and we'll go in hand to hand. As my sincere suggestion as well as request also for the participants. Yeah. So design development and multi-channel interface with the wireless and conducting power capabilities.
Yeah.
Some disturbance.
Yeah.
Okay. I think this title itself is some sort of a advanced title of this charging infrastructure. So, but let us see what is there inside, and I will try to make you to understand. So today I would like to talk about what is the motivation behind this EV infrastructure, especially charging infrastructure, and I will give some idea about conductive charging as well as wireless charging. In the wireless charging also there are different verticals, starting from inductive wireless power transfer to capacitive as well as hybrid wireless transfer. Maybe it's a combination of inductive as well as capacitive nature.
and this is the one of the next generation charging infrastructure. Most of the charging infrastructure we see currently across the country as well as across the world, most are related to the conductive charging. So inductive charging or wireless charging also have a lot of potential, and some of the countries, especially Western countries as well as European continent, if you look at, they are in the research stage. Maybe in the upcoming days, we can also see this type of charging infrastructures in the market. Okay. And next, I would like to give some idea about research activities and EV laboratory, IIT Bhubaneswar. And we carried out some of the research on these wireless power chargers. So the findings I will try to present as a part of the proposed systems and their analysis and some sort of parameter design as well as zero voltage switching and all. Dynamic response followed by experimental validation. So this is the idea, this is the work carried out by one of the PhD students. But maybe I think because of the heterogeneity of the people, I will highlight the findings rather than going a little bit in depth. And also, maybe if you are having some doubts in between, please raise your queries as well. I will try to address them. Yeah, mostly this is related to the research topic rather than generic way. So I expected something like faculty development means a little bit in depth only. That is the reason why I prepared in that manner actually. Yeah. So if you see the integratory part of this EV ecosystem, why nowadays people are saying that why EVs are needed and all. This slide is talking about that. So one of the main motive behind these EVs of that is environmental pollution. Look at the right hand side. So we have a bar chart here. So global greenhouse gases emission by each sector if you look at. So transportation sector especially is contributing to almost 20% of the pollution. Okay. So rest of the sectors you see, maybe we are giving here industrial sector, agriculture and so on. So this 20% from the transportation sector, basically from these vehicles most of the times. So how do you address this 20% emissions? So one of the way forward step for this one is deployment of electrical vehicles. That's only the research trend if you can look at. So how do you see really is it only the solution? So maybe in that aspect you look at, there is a survey from 2009 to 21 you look at. The sales of electrical vehicles. So in millions we look at the global wise, increasing trend, exponentially growing. So now 2023, 2026 we see is much more because of this oil prices and Iran war and all. There is a much deployment of electrical vehicles nowadays. Okay, so that is the reason why Indian government is also thinking right now something like why we are not investing the money into the research on EV sector and make the components, all EV components indigenously rather than importing from somewhere else. So that is the one of the motive. With that motive, Indian government has come up with the Mahakali programs. As I told you in the morning session. So I think 7 e-notes are set up by the Indian government. One is at IIT Mumbai, another one is IIT Kharagpur, and IISc Bangalore, NIT Surathkal. So there are 7 e-notes. Each e-note is accompanied by about 6 to 7 institutes. About 142 scholars are working in this domain, especially to build EV projects for the EV ecosystem in India. So you look at maybe hundreds of crores they spend on this program. So IIT Bhubaneswar also received about 10 crore for setting up of the EV laboratories. Charging infrastructure about 4 or 5 crores we have. So with that we set up some of things I will show you. Yeah. So but the idea is maybe right now. So government is also thinking in a better way on your EV ecosystem. So earlier maybe thoughts are something different because of these wars, crude oil prices and all. There are some sort of dynamic changes in the government as well. So that is the one of the takeaway point I would like to give to the faculty colleagues here. Yeah. And of course, you might have known the benefits of electrical vehicles, right? So, running costs and maintenance costs will get. I think some of the points are contradicting till now with the IC engines, especially in some aspects. Still, there need to be much more research, especially below, battery is the one of the backbone, but battery is still lacking in many aspects, especially when compared to the existing vehicles. Right? That research is still, we have so many bottlenecks. So this separate area, so we need to look at that also. So, but lower running and maintenance costs and efficiency wise, pollution and emissions. So these are the recycling of these batteries is also one of the biggest challenge. That's also one of the area we need to explore in India, especially how to do circular way of tackling these EV ecosystems nowadays. So that in that way also now research is also turning about, especially once after a few years we have a lithium-ion batteries, we have other technology batteries. Once we are using the batteries, how do you recycle them? That's the biggest challenge. Maybe some sort of programs, research programs are there, and fund is also given to the many people on researching how exactly you can recycle them without harmful to the society or whatever it may be. That programs are also going on currently. Yeah. So, but mainly the main challenges if you look at here. So the necessity of high power. I know, right? So thing is like once we are deploying the electrical vehicles, right? So then the power demand, especially the demand seen by the electric grid, if you see, is much more higher. It's like actually like a huge load sometimes. So high power and large capacity battery packs. Driving range is one of the main bottleneck currently. Correct? Driving range anxiety, what we are calling the technical terms. So maybe many manufacturers are coming and they are saying we are charging once we are getting about 150 kilometers or 200 kilometers mileage and so on. But maybe that is true for the two-wheelers. We are going for a bigger trucks. But so there are various limits of EVs, two-wheeler market, three-wheeler, four-wheeler, and so on. Right? So now this driving anxiety. Okay, if you wanted to get more driving, like more mileage, the way is we need to accommodate more batteries in the vehicle. If you are accommodating more batteries in the vehicle, and the weight of the vehicle is also increasing. Right? Once it is increasing, then again what is happening? Maybe mileage is also decreasing. This is one of the bottleneck especially. So I think there are some sort of the solutions for this problem, but now currently these are all in the laboratory levels only. We need to spend huge infrastructure to tackle this type of problems. So one of the way what people are tackling is through dynamic wireless power transfer systems. While vehicle is under motion, we are charging the vehicle with minimum energy storage system in the vehicle, right? So, but only thing is that our road infrastructure has to change a lot. So, but European continent, especially if you look at Japan is already planning to deploy such type of dynamic DWP systems, dynamic wireless power transfer systems. Okay. European continent also, some of the countries are working in the DWP systems. So range anxiety can be addressed to this one, but only thing is at a expense of cost. That's only one has to do with it actually. Okay. But in India, you look at this DWPT concepts and all, you look at it is a long way to go. It's not so easy actually, but still research is going on and government is spending money on this for researching the technologies in the especially DWPT and so on. Exploration stage only, not in the market especially. So we are exploring the things for the Indian market nowadays. So I think that is also one of the research area one has to spend. Maybe somebody working as a research areas, DWP is one of the potential area. There are so many explorations we can see in that area. I have few slides at the end. I will also throw some light on what is DWP, what are the outcomes of this DWPT in our laboratory and all. I will explain. Maybe we set up about 5 kilowatt dynamic wireless power transfer setup in our laboratory. I will give you some idea about that. Yeah, so next is like especially long life, cycle life and see battery. Researching on battery is also one of the vertical we need to concentrate. And finally, reliability of the entire EV ecosystem. So this EV ecosystem is built on electronics most of the times, power electronics and so on, everything, right? So reliability of these power semiconductor devices. So nowadays people are using silicon carbide and white bandgap devices and so on. So the vehicle is experiencing different drive cycles. How this electronics is also seeing the variations in the temperature and all. So we need to monitor them properly. That reliability aspect is also one of the key parameters to see the life of EV ecosystem. So that is also one of the main challenges that are currently. Okay. Yeah, so this is some of the challenging issues. I think if we have a SRKREC asset researchers, those who would like to carry out their research, especially on these EV subsystems, this reliability is also one of the key aspects. And there is a much scope for the findings in the reliability. I'm sure about that. Few researchers are working currently in this area in our country. Yeah, I think moving forward, we see especially on tracking, mostly on this EV charging infrastructure, correct? So as I told you, there are two types of charging infrastructures. One is the conductive and another one is the inductive or wireless. Okay. Conductive case, I think people might have experienced already these two-wheelers. So when you are charging your vehicle, what are you doing? You are taking the cable and you are plugging into the socket, right? So then we are using some sort of a longer cable. For two-wheeler, it may not be a big headache, but really if you are going for four-wheelers or trucks and so on, sometimes what happens is the size of the cable, and also the locality of this cable is very tricky. These are all some sort of, one is like environmental wise and another is safety wise. These are some disadvantages, especially when you are using long cables and so on. That's the reason why what people are proposing is you can also do charging through wirelessly. So one of such attempts is wireless power transfer technology. So it is not a new technology. Maybe you might have known Nikola Tesla and these people who have carried out long back, right? But the thing is, during that time, the efficiency of these wireless systems are very low. Later on, MIT did some researching a few years back, and there is a push for the research on EV wireless power technologies. only few researchers. Okay, so that point I would like to highlight wireless power transfer systems here. Yeah, so we are using some sort of a long cables. Okay, there are certain disadvantages. So then instead of going with the long cables, you can also see some sort of alternatives to charging. What we are saying is to wireless without connecting any wire. I think this is simply like if you know about the transformer operation, correct? The similar way what we are working here. In case of transformer, we are using some sort of a core, right? Primary coil is there, secondary coil, primary winding, secondary windings are there, and magnetic flux is guided by the core. But here we are not using core, in fact, we are using air core coils. And maybe we are keeping some current force not connecting properly. So that ideas are also there in the research. But loosely coupled coils what we are using here mostly. But the principle of operation remains same like a transformer itself. Yeah. I think as I told you that disadvantage of cable are highlighted here. Long, bulky and heavy charging cable, safety issues with the wire charging, some of the points are given in the research here. So that is one of the motivating factor for this wireless power transfer technology. And as I told you, I think it is not a new area. 1996 itself, Tesla coil, if you remember, we conducted some of the experiments and we saw this idea, especially wireless power transfer technology idea in 1986 itself. You can do the one. So, but nowadays you see, we are researching that two ways. One is like a near field coupling and far field coupling. Near field coupling led to resonating based technologies what we are using. Far field, you see microwave, laser and all what people are proposing especially. Okay, right. So now, if you see near field, there are various applications. So that applications, you look at consumer electronics, especially you look at your cell phone. So sometimes you are charging through wire. Sometimes some cell phones are there through wireless, also they are keeping on your watch. You can also charge through wireless. But most of the time they are using a technology called as capacitive wireless power technology. So, and that comes under consumable electronics. Maybe we are going with the EV, biomedical applications. There are various applications for wireless power technology, but maybe the designing of the systems are different for different technology. But if we are talking about the EV charging, so that design and upgrading them to the scaling them to the required power level, these are the main challenging issues here. One of the other challenging issues we look at air gap between the chassis of your vehicle to the ground. Okay, so that air gap is also one of the very challenging issues. There are some sort of guidelines for this. How much air gap we need to maintain according to the standards of automotive industry. So that one has to follow while you are designing the coils, you are designing your power electronic systems and so on. So that guidelines are very much important as a researcher actually. Right. So maybe we are starting in a generic way. So we are starting something. So we are, I think, I'm discussing with Varma sir. So starting is something different. Learning of skill is something different. This experimentation is something all the way you need to learn as a researcher. So I think some people are doing research on some of the algorithms through computers, maybe computing methods and all they are using. So that is another research area. Maybe they are contributing to some other area. But those who are attempting the research, especially on these power electronics aligned areas, they should have exposure to skills, hardware skills and so on. This is what I am trying to make one point here. Yeah. So these are the applications especially. Okay. Consumers, biomedical and so on. So, but in case of transformer, primary winding is excited with a power frequency 50 Hz, correct? That is what we are generating in India. But in case of this wireless power chargers, this primary winding and secondary winding, combination what we are calling as a magnetic coupler, these are not excited with a 50 Hz voltages. Okay, these are excited with 85 kHz voltages. Okay, so what is the reason why we are going with a excitation of 85 kHz?
Wireless transmission.
Wireless transmission. So is there any idea, any of you, why you are going with a high? Normally EV, especially I am saying EV case, if you are using a charger with a wireless power technology, inductive case, inductive wireless power transfer, IPTs, there is a range of frequency band 79 kHz to 91 kHz. This is the band given by the task force, the automotive industry, for the automotive industry. This is the band. Why you are choosing that frequency for the excitation of these coils? Anybody, do you have any idea? Right?
Why exactly 79?
Why exactly 79 to 91 around? Center frequency about 85 normally people will take. Any idea?
Size and weight.
Size?
And weight.
Size and weight, yes. One, size and weight. Any other points? Fast. Transmission capability. Transmission capability. Fast charging. Frequency. Yeah. High frequency means fast charging. Yeah. So 3 points I think we got from our colleagues. Yeah. So one of the first reason, if you look at, I think so every, you see, applications, especially radio frequency, people will talk. What is the radio frequency? So I think there are certain bands of frequencies, right?
Megahertz.
Megahertz, right? Some bands of frequencies are given to some applications, right? So if you don't want to interface with that such type of applications, you need to have some band of frequencies for wireless power transfer also. That is the first motive. So for EV domain, especially IPTs, task force coming up with a domain frequency range about 79 to 91. This frequency band may not be applicable for other frequency, other applications especially. Okay. So, but this is IPT range. But if we are going with some sort of a CPT, capacitive wireless power transfer, their bands are a bit different. You cannot work capacitive wireless power transfer is also basically not a racket technology type of thing. It is a layman sense. You see, there are two plates are there, and there is a dielectric charges, right? Charges, maybe electric fields what we are using to transfer the energy from one plate to another plate. Here magnetic field is energy, right? So same concept, but why you are using, see, capacitive, if you wanted to make air gap between one plate to another plate, maybe normally look at in case of wireless power transfer, especially IPT, standardization, if you see, 100 mm to 250 mm, 100 mm to 250 mm is the gap between the primary and secondary. Okay, primary secondary means your vehicle. You see, vehicle you are keeping a secondary coil, and ground you are keeping the primary coil. The gap or clearance between the two coils, if you look at, is normally 100 mm to 250 mm. This is the standard. So why I am calling 100 to 250? Why I am not specifying one number? This is based on the class of the vehicle. Z1 class, Z2 class, Z3 class. They divided. Okay. So if we are going with a two-wheeler, there is some sort of a clearance. Three-wheeler, large trucks, there is a difference. So if we are transmitting huge amount of the power, based on the power also we are dividing this wireless power transfer technologies. Suppose if we have a power rating of our charger, EV WPT, I can call right now onwards WPT, wireless power transfer technology. WPT chargers. So 3.7 kilowatt charger below 3.7 kilowatt is called as a level 1 charger. 3.7 to around 11 kilowatt. Okay, around 11 kilowatt. Maybe what we are calling as a level 2. More than 11 kilowatt chargers, what we are calling as a level 3. See, there are different standards, especially. I am talking about SAE standards, right? Automotive standard. But there are other standards also. So every standard is defining different power levels, and distance is also varying. Maybe I have some slides, I will throw it, but just for giving some sort of idea, the main key points related to this EV is, one is the air gap, right? Jet class, what we are calling. Another one is power levels, level 1, level 2, level 3 chargers, correct? What are the power levels and all? These are defined by the EV automotive industry. And third one is, what I told is a frequency band. IPT already they set up the frequency from 79 to 91. These are the three or four important points as AV engineer in do. So next one is, the CPT is not working with the same band of frequency, capacitive. Because you look at capacitive plates, the main medium to transfer the energy from one plate to another plate is the electrical field. Correct? If it is the so, then you see that the gap between that two, you see the coupling capacitor, what we are calling that. The coupling capacitor is normally the CPT system you look at is in the range of 10 to the power of minus 12. 10 to the power of minus 12 farad. Okay. So picofarad range, the coupling capacitor. But if you normally the power transfer, output power, if you are giving some input to the capacitor, you are getting some output. Output from the output power from the capacitance is a function of this coupling capacitor, right? So if this value is in the range of 10 to the power of minus 12, then I may not get the power. I wanted to get the power in terms of kilowatts. How do you get it actually? I may not get that. This power is normally proportional to the coupling capacitor, switching frequency, and other parameters. Unless otherwise I am going a switching frequency is more than megahertz range. Megahertz range, I cannot achieve a moderate power transfer to capacitive plates. That's the one of the reason why capacitive power transfer is going with a high frequency ranges. Maybe till now, many people, those who are working on pure power electronic converters, they are just developing the converters and they are finding out the efficiencies at some kilohertz and so on, correct? 100 plus 200. But real applications, if you see megahertz ranges, so converter should operate at megahertz, and at the same time it has to handle the power rating about few kilowatts, 10 kilowatts, 20 kilowatts, 30 kilowatts CPT systems. If you wanted to do, really that is the challenge. At megahertz frequency, transferring of that amount of power is not a simple way. Okay. So our dedicated circuits you need to devise. And dedicated circuits with sensing of the megahertz voltage, megahertz current, these are challenging issues especially. It's not so easy. Right? So you need to have a dedicated operational amplifiers for them and a dedicated microprocessor. We are talking about DSPs. The DSPs also has to have a processing speed of megahertz, more than that especially. So these are all some of the challenging issues in the CPT, but still people are doing research and there is a progress on the CPT side also, hybridization of these two also. Okay. So the main takeaway point from the CPT case is that the operating frequencies for the capacitive wireless power transfer is much higher than the IPT, inductive wireless power transfer, because the coupling capacity values are in the range of picofarads. This is one of the main takeaway point. Okay, right. Now, yeah. So coming to here in this slide, IPT. I think there is a flow diagram, or maybe you can say this is a block diagram. I hope you are able to see this, right? Huh? Right. Yeah. So you look at here, there is a power supply, right? Grid. Right? So maybe after that, so we are using some type of inverter. Okay. So as I told you already, magnetic couplers, primary winding and secondary winding, these are loosely coupled. I am not connecting any core there. I think you know about the transformer, right? How many people know about the transformer? I think most of you. Good. Then. Right. So then, in case of our power systems, this primary coil is excited with a 50 Hz sine wave. Yes. Correct? Now we look at, but in case of inductive IPT system, you are not excited with a 50 Hz as I told you. I am going with a 85 kilohertz. But 85 kilohertz is not a sine wave. It's a square wave. I am exciting the primary coil with a 85 kilohertz square wave. Why not with a sine wave? Anybody? Why not with a sine wave? Harmonics. Right? Same harmonics. Range is 50. How do you generate this sine wave? Sine wave generation, you know, 50 Hz sine wave, how we are generating synchronous generators in that, right? But 85 kilohertz sine waves you wanted to develop. What is the idea? Getting power electronics to like that. Cyclo converter.
Well, using cyclo converters, we don't expect the perfect sine wave.
We cannot expect it from cyclo converter. Any other points for the discussion? Our colleagues are saying cyclo converter and some like anybody, I think some people are from power electronics side as well. Maybe you have some ideas about how do you generate the 50 Hz, 60 Hz, 20 Hz, 10 Hz sine wave from the inverter? How do you generate? You know, inverter. If you have inverter, how do you generate? Through pulse width modulation, correct? What are we doing, especially sinusoidal pulse width modulation or something like that we are doing, and we are generating different frequency. So inverter means what? So you are applying a DC voltage, you are getting a AC, right? That AC maybe I can change. AC means magnitude of the voltages, frequency of that voltage, and phase angle of the voltage also I can change, right? Vm sin omega t plus or minus pi. So Vm I can, magnitude I will change, frequency omega I can change, pi, phase angle with reference to some arbitrary frame also I can change from the inverter, correct? So that is the idea. Sine wave I can generate. If it is from 2 Hz to around 50 Hz, 60 Hz up to 100 Hz and so on. Okay, I can change low frequencies is fine. Right? Low frequencies is fine. But so if you wanted to generate the 50 Hz sine wave, why? You are generating variable frequencies from the inverter. So especially if you are going with the drives applications, V/F control, vector control, or maybe scalar control, whatever we are talking about. So this V/F is on the key, correct? Flex. Yes, control speed. Some sort of multiples of this fundamental, correct?
But is it sustainable, sir? Is it sustainable, sir? Is it possible or sustainable?
So you are saying 50 Hz? No.
Here, up to 58 it is okay. All the things are good.
I am coming.
But when for 85 kilohertz, is it sustainable?
That only I wanted to give that point. That is the reason why. Yeah. So I think. So what is happening is 50 Hz is fine. 50 Hz means 50 into 20. How much you will get normally? 50 into 20, 50 into 1, whatever it is, times. Where 50 Hz means 10 kilohertz or 20 kilohertz, kilowatts is fine. No problem. But if you want to generate the sinusoidal voltage with the 85 kilohertz, so how much? What is the carrier voltage frequency? It should be 20 times, 30 times of the 85 kilohertz. So switching frequency of a device should be in terms of megahertz. And also if you are switching the power electronic devices at higher frequencies, the main problem is switching losses. So efficiency of your system is gone down and thermal aspects, designing of thermal, taking of this power, thermal power, switching loss are converted to the thermal, right? Thermal losses, temperature, taking away of the temperature, heat sink design, these are all big headaches. Correct? That is the reason why generation of 85 kHz sine wave is not advisable, it's not a good idea. Okay, in this aspect, that is the reason why you are going with a generation of square wave with 85. But can I generate 85 kHz square wave and I can give? Can I get it? Suppose why I am not generating the square wave through 50 Hz square wave and I am not using the transformer. Generators are meant for 50 Hz sine wave, we are generating. Okay. But I can also generate 50 Hz sine wave, right? 50 Hz square wave and I can. But see, there is a difference between the 50 Hz square wave, 85 kHz square wave. So your friend is talking about the harmonics, correct?
Yes.
Okay. If you are going with a higher switching frequencies, the magnitude of higher order harmonics you look at. Your fundamental is sitting at 85 kHz. If you are going with a 3 times the fundamental, 5 times the fundamental, and so on, 85 kHz central frequency. So higher order harmonics in the 85 kHz waveform are not much dominating. We will consider fundamental approximation, especially high frequency square wave contains most of the fundamental when compared to the higher order harmonics. So that is the reason why 85 kHz square wave is generating and we are feeding that to the
Sir, not with the help of filters we can eliminate the higher order harmonics also.
Right.
But lower order harmonics there is an issue. There is an issue with the lower order harmonics.
Lower order maybe 50 Hz square wave we are going, but lower order aspect third harmonic, fifth harmonic, not significant magnitude. But 85 kHz we are looking at the small capacitance or the inductance. What we are using compensated capacitance, I will discuss later on. The small capacitance is enough to eliminate all the high order harmonics at high frequencies. That is one of the idea why we are going with why we are generating with the 85 kHz square wave rather than sine wave. The difference. Maybe I will come with that. How we are getting a sine wave out of this 85 kHz in a simple way. So,
Sir, we generated so-called 85 kHz frequency using cellular signal.
Yeah. So 85 kHz. Normally, what people are using is cycloconverter using that. So if we are using a wide band gap devices, except maybe I can use a silicon carbide devices. I am just acting like a HBs, like inverter only. Inverter with a simple principle, phase shifted modulation principle. Phase shifted modulation means what are the inverter doing? Maybe this is a new term for many of them. Like maybe you have a 2x. I think I will show you. But for your question, right away what I will point out is it is like an inverter, not like a cycloconverter. So that I will say right now. When I am going there with the operating principles, I will discuss now exactly we are coming up with the 85 kHz voltage for the DC.
What is the maximum frequency we can shoot up using the inverter? What you have?
So maximum switching frequency is decided by the switching device, especially silicon carbide when you are looking here. So adaptive switching frequency is the one of the main criteria. Another one is the power handling capability of the device. So suppose maybe power handling capability also you are selecting a device for the 11 kilowatt application. So 11 kilowatt it is able to deliver 11 kilowatt with this issue. So 11 kilowatt means your voltage of your switching device is 400 volt. Okay, lagging voltage especially I'm talking. And your forward current rating is about 100 amperes. 400 into 100 is the kVA rating of the switch. So if it is having that much of kVA, that is issue. So then I can tell you the power, but switching frequency is decided by the switching device. Silicon carbide when you choosing, silicon carbide device normally can operate about safely 100 kHz, 150 kHz. Silicon carbide 100 kHz is also fine. But I think the applications people are proposing to go with 85 Correct. 85 kHz is standard, that is the number. A centered frequency of 85 kHz I am operating this system. You can also go with some kind of other galvanized device and all. GAN device. That is also one of the ideas. Okay. But the best suited device right now, what people are researching in the CP technology is silicon carbide devices. Silicon is powerful, of course. Silicon MOSFETs are there. You can also operate them up to 100 kHz. Silicon carbide, why it is rising? Some sort of advantage over the silicon devices. We are coming to the silicon carbide and losses and all, especially in the carbide. So silicon carbide is one of the dominating device currently. Okay. Gallium nitride also people are using GaN. Okay, no problem. But power ratings are restricted nowadays. Yeah. Yeah. So this inverter. This inverter is meant for DC to AC. With 85 kHz, converts 0 frequency to 85 kHz, and that 85 kHz voltages, before feeding to the magnetic couplers, they are feeding to the compensation networks. What is the compensation network and what is it? You see, I am saying some compensation network here. Okay, so I think you know, right? So you have a magnetic coupler, primary and secondary. There is no magnetic core, right? Why you are using core in the transformer? To guide the magnetic field, right? The coefficient of coupling is checked. 0.9 coefficient of coupling. Leakage fluxes are low, correct? But when we are talking about the loosely coupled coils here, air-cooled coils, so when you are exciting the coils with certain voltages, there is a magnetic flux in the primary magnetic flux may not link with the secondary. There is no flux guidance, there is no core. Leakage fluxes are very high. If leakage fluxes are high, you cannot transfer the huge amount of the power from primary to the secondary. Mutual flux should be there. Correct? If the leakage flux is there, then maybe coefficient of coupling of these WPD systems you look at especially, it is ranging about 0.1 to 0.3, but transformer case you can say 0.9 to 95, 98 energy. Right? Here 0.1 to 0.3, very loosely coupled coils. Huge amount of leakage flux is there. But how do you address this problem? This problem can be addressed through by keeping such type of compensation networks. Okay, we will keep the compensation network and we will create some sort of a resonance, electrical resonance there. Okay, so you know very well, right? In the power system sense, the power system sense, how are you generating the magnetic fluxes normally? A reactive power supply. Through reactive power, I can generate the magnetic flux. Correct? Right. So that is the case. Here also you can thought of if leakage fluxes are higher. From the inverter can generate the reactive power as well as reactive power. Okay. But leakage flux is high means most of the inverter output will see as a reactive power only. Reactive power only. If reactive power generated by the inverter is higher, what is the problem? The problem is efficiency. Efficiency of your wireless system is very low. Reactive power is high. I am not maximizing reactive power. Correct. So how do you minimize the reactive power here from the source? Source means from the input side. So through compensation networks. Correct. I am keeping some compensator. The compensator will generate the local reactive power and it supports the coils. Okay. Or otherwise, in the other sense, I can say this compensation network will create some sort of a resonance and it will enhance the power transfer capability of wireless power transfer network. Okay, these are two ways of seeing the problem, right? So,
why can't we use conventional code winding system rather than going for air code?
You
To
see,
avoid all these complexities.
so especially when you are tackling about transformer and all, you have a core structure, something like connecting with a primary and secondary. Primary and secondary, and there is a connection through magnetic core. Correct? So if you look at the vehicle, if you look at the vehicle here, so this is the primary side. So here I am keeping the primary coil, here I am keeping the secondary coil. Okay? Vehicle I am keeping the secondary, and the ground I am keeping the primary coil. I wanted to connect them. If you are making some sort of a magnetic core connecting the primary and secondary, then maybe the connection is a little bit difficult here. But people are using. How they are using? Are not connecting directly. So they are keeping some of the ferrite bars. Ferrite bar means this pores under the primary coil as well as secondary coil to attract that flux, most of the flux. But the problem is, you see, when you are keeping a ferrite pores, they are using some sort of 85 kilohertz, right? 85 kilohertz frequency. But ferrite will work nicely up to 100 kilohertz, 150 kilohertz, and so on, right? 100 kilohertz and so on. But sometimes what happens is if the power rating and current ratings are drastically changing, ferrite may saturate also. In the saturating, we lose some sort of functionality of the charger. But people are researching with these cores also, but the location of the cores and all it is different, where they are keeping and all is different. I will show you some idea a bit later. But not like a conventional transformer. You cannot keep like a conventional transformer connecting the primary and secondary coil. These designs are completely different, but the ideas remain same. Designs are different. Yeah, so we are keeping a compensation network to the primary. So we will also call this entire part as a transmitter, like in case of communication systems, transmitter. So basically, this transmitter is sitting like a primary, and it is sitting on the road or parking lot, right? And the second part is the receiver. Receiver is sitting on the vehicle. Okay, the vehicle. So coil, compensator, power transmitter, rectifier, and batteries. What is the idea? The main idea is you have a grid, especially a distribution system, and distribution system voltages are converted to the DC, and DC voltages are available here, and through inverter I am converting that into the high frequency voltages, and high frequency voltages are cutting to here, correct? After that, energy is transferred from primary to the secondary, the receiver again compensator, and high frequency voltage 85 kilohertz voltages are converting back into the DC through rectifier. And batteries are sitting anyhow, battery needs DC, that DC power only I am feeding. Okay, that's the idea. So this is one of the overall system of IPT, correct? But if you see conventional charges also, you can see more or less this type of structure only, but some of the components are not here actually. So what is the conventional charger? Conventional charger contains, you have a distribution system. Okay, like you see your scooter itself, EV scooter, you have a plug and inside the lock box is there and you are connecting that, right? What is the lock box contains? Your converters, correct? Converters, some isolation transformers and all is there, correctly, right? So in the similar flow you have, that is you have some sort of a DC there, where if you look at AC to DC is there, and finally DC we are giving to the batteries here. But in the wireless power transfer, you have these components here. Okay. And the capacitor also similar type of structure you see, but inductive couplers are replaced by capacitor couplers here. That's only the difference. But the design and all, the black diagram way is same, but really if you go for internal structure and researching of the components and all is completely different. But the black diagram more or less is same. Yeah, so the points what I related, same thing is there. And other things. Yeah, so if you see layer wise, especially how these coils are appearing in the ability systems. Okay, these coils are having, these are the couplers, as I showed you here, couplers. So these couplers are like this, especially if you see a real couplers. What we have here, if you see, This is a coil. Okay, coil means we have a copper wire and we have one. This copper wire is not like a normal copper wire. You know, I think we have a copper wire, right? So you might have seen your cable with the insulation. We have, right? So we are not using such type of copper wires. So we are using some specialized wire called as a lidge wire, L-I-T-J, lidge wire. Why we are using lidge wire? For wireless power transfer applications or otherwise power electronic converters where we are using as power electronic converters high frequency, we prefer lidge wires rather than conventional copper wires. What is the reason? Anybody? Did any of you saw the lidge wire? No, right? So lidge wire is nothing but some sort of a bundled wire, bundled conductor. You know, bundled conductor in the power system you look at, right? So you have many strands, correct? So in a similar way you can see here, lidge wire contains thousands of strands, small strands. To tackle the skin effect, especially high skin depth, you might have known 50 Hz system you look at, we are going for the bundling of the conductors in the transmission systems and so on. Why you are going with that? In order to handle the skin depth, skin effect, correct? So, like you know very well, right? So when you are passing DC current with the coil conductor, uniform current density you can see across the conductor, right? Everywhere uniform current density. Okay? But you look at in case of AC system, AC when you are passing through a solid conductor, most of the current density is concentrated on the outer layer. In the part, you cannot see any current. The utilization of the current density is not, utilization of the conductor diameter is not up to the mark. Right? And what is the other technical drawback, especially the main technical drawback is AC resistance of such type of conductors are higher, much more higher than the DC resistance. I think you know, correct? So only current density is concentrated on the outer part, AC resistance part is increasing. AC resistance is increasing, isotope losses are increasing. That's the problem. But if you are tracking that with a 50 Hz system, correct? But 50 Hz system, AC resistance is something different, skin depth. But if you are talking about the 85 kHz, 85 kHz, the wire strand diameter, if you look at, it should be very less. That is why thousands of strands I am using. All strands I connecting them as a one conductor, and I am passing current to tackle these losses, especially skin losses and all.
So what about voltage, sir?
Yeah, so voltage that you see, even I am applying about, look at here, through this inverter input, I am applying 100 volt. Okay, 100 volt. So, inverter output, you are getting a square wave, positive 100 volts, negative 100 volts, right? 100 volts to the excitation coils. Okay, but the coils may not see this 100 volts. Before compensator, I am applying. See, before compensator network, I am getting this wave here. But these coils will see some sort of a kilovolts. What we are doing is, you might have seen the case of series resonance, parallel resonance circuits. What exactly happening in the resonating circuits? Magnification of voltages. Q factor, right? Q factor, I think series resonance we are talking. Voltage, suppose 10 volts. Q factor is 10, 10 into 10, 100 volts is appearing. Suppose 100 volts, Q factor is 10, 1000 volts is appearing. Like what I am doing is, I am creating a resonance, and through that resonance I am magnifying the voltages. That voltage only I am applying across the coils. If you are applying a larger voltages to the coils, the transfer of energy is also higher. But I cannot create such type of voltages through inverter. If you are creating that much of voltage to the inverter, switching devices size and all is much more higher. Okay, one device with 3000 volts, much more cost. That's the reason why I am keeping energy storage elements like a inductor and a capacitor and creating a resonance, creating a high voltages in order to transmit the transfer the high value of the power. Okay, so the basic idea is here. Yeah. So you have a copper wire, bridge wire here, and we are making some sort of inductor here foil. I think we made in our laboratory. I will show you. And below that, we are using some magnetic core, as I told you. Ferrite cores also people are using. Okay, and next the aluminum shielding also people are using. You see, two coils are kept like this, right? So aluminum shielding at the bottom. So receiver coil top and transmitter coil bottom. They are keeping aluminum shields. Why aluminum shields are using actually? You see, every coil is associated with aluminum shields, top and bottom. Why? So here, whenever you are exciting the coil with 85 kV voltages, as per the basic class what happened, magnetic field is set up with 85 kV, correct? That magnetic field, maybe if there is a current pass from here to here, there is some sort of a less reluctance and leakage fluxes are less, compensation requirement is. Okay, there is a flow of the flux, right? Flux guidance is there, right? But if flux guidance is there, then what is the necessity of these aluminum shields? Up to that, okay, leech wire and magnetic core, it is fine, correct? What is the necessity of this aluminum shielding? I think name itself is saying, right? Shielding. What is that? What it will do, right? What it will do is, you have a straight magnetic fields. What do you mean the straight magnetic field? You see, we are using a concept of Lenz's law. Most of the applications we are using this type of things especially. So what exactly you are doing is, you have a 85 kV voltages here, right? And that voltages will generate flux, that flux will leave the secondary coil. That flux again, what it will go, the circular fashion will go. Okay? So infinite circuits it will go. That is going in a infinite path and it will hit the chassis and those who are sitting on the vehicle also. Correct? There is, according to the standards, you should not go, you should not induce so much of radiations through these magnetic fields. You need to arrest them. How do you do? Through this aluminum shielding. What it will do actually, aluminum shielding? Whenever a magnetic field hits the aluminum plate, okay, what is happening? What is happening? When it is hitting the aluminum plate, there is a eddy currents. There is a magnetic field. That magnetic eddy currents are within the aluminum plate, so that that eddy current itself generates its own field. That field is opposing the Lenz's law actually. So it is opposing and it will counteract. It may not allow the current fields to flow out of this aluminum shield. It will capture there itself. So that is the reason why maybe through Lenz's law principle we are arresting or we are shielding the magnetic field. We cannot go within that shielding itself. There is a rotation of the magnetic fields there. That's what is the idea of what shielding is here. And yeah, these are 3 layers normally you can see in the standard coils. Apart from this coupling points and compensation network, coils itself have standard coils installed. And another important point is, you see that your vehicle is going on the parking lot for the charging. There should be a communication protocol from chargers to your vehicle, right? You are using some off and you are doing some other things. That communication also coming into the picture here, the communication model. So normally according to the standards, this type of ground assembly is called the vehicle assembly. Yeah. So this is the overall idea about the wireless power transfer actually. And when you are looking at the compensator, I told you, there are currently some compensation networks. Okay. Series compensation. Okay. So what we are saying is, you see, is exactly Yeah. We are talking about this network. So it is supporting some sort of a reactive power as I told you, right? So what exactly we are doing here, what exactly we have here is, there are different types of compensation networks. SS, series parallel, parallel series, parallel. So, you know, this, why do you have different variants of the compensation networks? Based on your application. Where do you need constant current output from the charger, constant voltage from the charger, so or sometimes constant current and some constant voltage. So that characteristics, if you wanted to realize, networks will be useful for us. You know, in case of charger, what exactly we will do it? If you see battery, so there are two modes, right? Constant voltage, constant current. So initially, if the battery, if you wanted to charge, the SOC means state of charge in the battery is about 20%. I wanted to bring that battery charge to 80%. What I will do, first initially, I will use a concept of C rate, capacity rate of the battery. Right? Based on C rate, I can pump as much energy as possible into the battery. A constant current. Suppose the battery capacity, the layman says if battery is allowing 20 amperes of current maximum, I can pump 20 amperes constantly for a longer time to reach the 20% SOC to 80% SOC. Constant current. Once it is reaching nearer to 80%, what I will do? I will change the mode of the charges from constant current to constant current. So such type of characteristics can be realized in the charger itself. I can reconfigure with some of the things, maybe control algorithms or some software. I can change from constant current to constant voltage. Right? Again, even your cell phone charger also that is happening actually. So that's happening actually. Right? So once it is reaching to the 100%, total isolation is possible. There is no charging. The current becomes zero and there is no charging at all. Right? Yeah, based on activity, I am not going into the compensation capacitors and their analysis here. Just I'm highlighting why we are using different type of compensators means based on this site. Whether I are relating voltage characteristics or current characteristics, based on that we are dividing them. There are hybridization also techniques, LCC and so on. Yeah, so we look at this one especially. This is one of the earlier block diagram only. We are expanded that and we are going into the what is there exactly in each block diagram. Each block. So this is the AC voltage, distribution voltage, and this is a front-end rectifier. What front-end rectifier will do? AC to DC. Correct. We are converting AC to DC. Okay. So I need a DC for high frequency inverter. Correct. That is the reason why I am using a PWM rectifier here. I am converting AC and DC to DC. They are also converted to DC. And these DC voltages I am applying to a high frequency inverter. I am calling that HF5, high frequency inverter. What it will do? DC voltages are converted into 85 kilohertz AC voltages. And AC voltages are square waves or quasi square waves. Correct? And after that I am using a compensation network. Like as I showed you, series and series parallels, a type of compensation network. And there is a magnetic coupler, primary coil, secondary coil, coupling is here. Right? And again, same compensation network is there. These are vehicle, this part is sitting on the vehicle, this part is on the ground side. And high frequency voltage is again converted back into the AC, DC through rectifier. And DC, through that I am charging the battery. Correct? So the idea you see, so this is called as a high frequency link. We are operating this one at a high frequency 85 kHz. 50 Hz voltage is converted to the DC through high frequency link. So, and so why we are calling this as a wireless power transfer actually, primary side, ground side and vehicle side both are isolated through this inductive coils. There is no direct connection, there is only connection or this transfer of the power is taking place through magnetic coupling, not like the electrical wiring or whatever wires what we are using. That is the one of the point here. Yeah, so engineering of all these components is the main key part for researching this wireless power transfer, right? So yeah, so same thing you see. If we have some sort of a controllable converters, here controllable switches are there, then you have a primary controller, secondary controller. As I told you, see, this is the high frequency inverter. How are you getting a square wave from that a simple H which here? Look at. So there are 4 switches, one leg, second leg. Correct? You know, I think those who are teaching this power electronics or basic knowledge of power electronics will understand. This is the DC voltage. Okay. That DC voltage is converted into this type of AC voltage. Alternating voltage, positive voltage and negative voltage by making use of this converter. There is the one leg and this is the second leg. How are you doing here? You see, and S1, S4 both are on. These two are on. So what is appearing between these two terminals? You see, you see this and this are on. So this is seeing the positive and this is seeing negative. And positive voltage is appearing here. Correct? Off diagonal switches are on means positive voltage, this voltage. And diagonal switches are on, these two are on, this terminal. Okay. This terminal will see positive and this terminal will see negative voltage will be there. This is a simple diagonal switches and off diagonal switches when we are switching on, you will get a square wave. But how are you getting that? How are you finding the switches? Okay, that is through some sort of a controller. This controller may be based on different platforms. Maybe it is through some microcontrollers using DSP, using some sort of FPGA platform. Maybe some control platforms we are using and we are generating the pulses. Correct? Yeah. So then, yeah. So that's our idea. Maybe here also you can control the power factor through. I can control the power factor here. Voltage and current increase through this controllable switches. At the same time, we are maintaining that. And here this side you see you have uncontrolled amplifier. Directly you are converting that into DC. So I'm feeding to that. And same thing I am highlighting. This part is exactly similar to this, and this part is exactly similar to this. Okay. So mathematically, we can also represent the system in this fashion. Okay. I think did you get this point? Did you get this slide? Yes, sir. Yes. Okay. So the main takeaway is the ground and the vehicle side. Okay. So there is a wireless points.
Sir, how the ground becomes one of the windings?
One of the
Windings. Then you can the other winding
see normally. So ground means you have a parking lot. Okay. You are using some sort of tiles. Correct. So your car is coming to the parking lot. And you are just asking your car to charge through wireless. Okay. What we are doing actually, so in case of conventional vehicles, okay, so charger is sitting on the pole of your parking lot, and they are hooking that into the car. Right? So, but here what we are doing is, instead of the charger itself, I am buried this primary coil inside the parking lot. I am removing some of the tire and then keeping some other arrangement here. Okay, I am keeping there. The coil and power electronic systems are connected like that. Okay. So then from there, so through electromagnetic field, secondary coil is sitting on the vehicle and then That's what we are trying. In the dynamic wireless power transfer, what happens? One coil is here, next coil is here, and so on. Vehicle is moving, dynamically you get the charge and the batteries. That's the idea. What yeah, so this is whatever the system. Yeah, so this is the overall idea. So now we are going to the what is research what we are doing at IIT Bhimavaram. So electrical vehicle vertical especially. So we are concentrating on this wireless power transfer along with renewable energy integration. You can see one of the vertical. The points only I would like to discuss. EV chargers. There are many sub-verticals here. So one is like a static next to wireless power transfer system, focusing on misalignment tolerance. Misalignment tolerance means, suppose you have a primary coil and secondary coil. They are not. So renewable energy plus dynamic wireless power transfer, these two aspects will combine actually. Okay. I think you might have known what is the concept of this dynamic wireless power transfer, right? Did you heard about this concept? So what exactly we are doing is, so if we have a 4-lane road, right? One of the lane, what we are keeping is charger pads. That means primary coils are sitting for 1 kilometer of short distance. Okay. So if your vehicle charge is less, you are traveling on the highway, and if your SOC of the battery is coming to 40%, I will go from power line to the line where these charging pads are there. I will travel and I will get a charge and I will come back. Like that, we will extend the range of the vehicle, mileage. So that's the idea. But building of such type of system needs heavy investments on the road infrastructure. Technologies are maturing, but building of the structure and all is very important for us right now. Some countries, as I told you, they are doing that things. Okay.
Is it available in India?
Japan.
Is it same principle?
Same principle. I think I have some slides I will show you that.
Has it been implemented ever in India somewhere?
No.
Not at all.
The exploratory stage only.
Okay.
Just we are exploring the possibility. But India is long way to go. Surely. But Japanese Tokyo University already set up some manufacturing companies, automotive companies. So they are ready. Ready means especially see, suppose if you wanted to go with the dynamic wireless power type of thing, you need to have modification on the vehicle side also. You need to keep your secondary coils there, and you need the road and all, isn't all there. That is the reason why people are already, some vehicles they are releasing with this type of arrangements also. Tokyo they are working, especially Japan, is the number one in automotive industry, so they are doing all these things. Western countries also, especially European countries also, some countries are working on it. thought about this Iran and other wars, right? Because of this wars, mindset of government is changing. Earlier, the mindset is something different. Now they are clearly telling indigenization of the ecosystem. Clear ideas they are giving right now. The government is also. Maybe that is the one of the path. Tomorrow suddenly some points will come up and that is the one thing. Yeah, so hybridization of conductive and inductive also possible. Maybe this is the one of the idea what we are seeing. So this is the one of the research topic. So that is carried out by one of the PhD scholar executive Abhishek. Okay, I think maybe you just spend the see and spend the time. So it is a little bit going into the research orientation. So this is like a modular series transmitter array based wireless charging system for multiple EV charging applications. Okay. So the idea is, you see, you have many vehicles, right? So this is what we are calling as a one wireless charger. Okay. This is the primary. All these primary pads are here, primary couplers, and vehicles are sitting in the parking lot. All vehicles are charging from this one power electronic converter fed by different drivers. Correct? So that circuit diagram we look at especially. So there are two configurations. I think you see this is on the ground, right? This is on the ground. Or maybe this is ground means this is located on ground and this is on the yeah. So then you see this system, the receiver is on the. So there are two configurations here if you want to charge multiple vehicles. First configuration, see, this is what we are calling as a power electronic converter system. What is doing? Nuclear supply is there, converting that to the DC to high frequency AC what we are doing is called as a power electronic converter system. As I told you. Right? So this is that box. That box is had a different vehicles. Different compensation network followed by primary coil. Second compensation network followed by primary coil, and so on. N number of vehicles means N compensation networks I am using. Correct? So this is one configuration. Configuration B you will get. In this case, what happens is instead of using N number of compensation networks, we are using only one compensator that is combined in the power electronic converter cell. You see here there is no compensator, but here primary compensator is coming here in this box itself. I am not keeping here, I am keeping here. And only coils are sitting here. There is no individual compensator. These are already addressed by the researchers. Multiple vehicles are there, how they are doing and how they are achieving the good charging efficiencies. And maybe these are all like in block diagram version. You look at here in the circuit diagram. Circuit diagram, what is exactly happening is, as I told you, you have inverter. Inverter, different compensator. Compensator 1, 2, 3 and so on. And coils are connected. Here, right? This is the one. And second configuration, this configuration B, what we are doing is, you have only one compensator. Like one compensator, all are connected in this fashion. See, DX1, DX2, DX3. They are connected. Okay. So these are the two configurations what people are using. That you have a multiple vehicles at the parking lot that are supposed to be charged by this wireless charged through wireless power transfer technology, right? So now some sort of challenging issues are there. What are the issues? Suppose you look at, you have a vehicle here, but you don't have vehicle in the DX2. Okay, sometimes 3 vehicles are there, sometimes only 1 vehicle is there. How do you manage them? Technically I am speaking all these things now. So So if that is the case, you need to have some switches SW1, SW2, SW3, and you need to see whether secondary coil is here or not. If secondary coil is there, then I will turn on these switches SW1, SW2. Otherwise, I will turn off. Okay. And also look at you have a inverter or charger. Every vehicle should get a constant output. Third vehicle, suppose two vehicles are charging, suddenly third vehicle come, other vehicle should not disturb. Okay. They should operate independently. Okay. So these are some of the challenging issues I am saying here, how to address them through these problems. Okay. Right. So this configuration you see contains multiple separate channels connected in parallel to primary. Okay. Includes dedicated compensation for individual PX coil needs channel. This configuration has channel selection features. Which channel you want, you can select SW1, SW2, SW1, SW2, SW3. I can select the channel. All channels are decoupled. I think decoupled means like independently we can work. While is through SW1 selection, SW2 selection, I can independently. High component count and high spacious. High component count means you see compensation networks are like more, and switches are also added, correct? That is the reason why component count is more. So, but this configuration B contains multiple TX coils. You see, TX means primary coils in series. But these are connected in parallel, these are connected in series. This configuration includes only one primary compensation network common to all TX, which makes less spacious. There is no channel selection, but I cannot select the channels here. Why? Means I don't have switches here. Channels are not decoupled. Not decoupled means you see all the current flowing through the channels you look at. So, suppose one vehicle is here, another vehicle is coming here, means maybe these two are interdependent. Okay. So, channels are not decoupled. Low component count and spacious switches. But we can address this problem through some other way out. So, what is the way out and all we look at? You see, this is the way. What the proposed here is that, you see, I told you first to get the DC is there, you need to convert it to the high frequency voltages, correct? That is the converter which is playing that role. We are converting to the high frequency voltages. And next compensation network we are using. This is the compensation network LCL we are using here. There are some advantages with this. This is a compensation network. So that compensation network output you see exactly. This is the one. This compensation network output here. Okay. This is the converter. The compensation network is the output. This is the one. That is called as XY. Okay. That is feeding to n number of series connected coils. Arrays. Okay. So each array, what we did is we connected some switches. But we have only one problem we highlighted. What problem we are highlighting? So the problem what we are trying to address is we are not using n number of compensation networks. Okay, that's the problem of highlighting. But still, see how do you achieve decoupling? Power decoupling and all that is through the switches. You see, SW1, SW2, SW so on, SW10. All are connected in series. One TX, second TX, third TX, and so on. And maybe see, this is a vehicle 1, channel 1 means vehicle 1 is connected here, channel 2, vehicle 2, vehicle N, and so on. Right? So this is what the problem, STA, series transmitter array type of configuration for n number of vehicles if we have, how we are charging to the common tax. Correct? Yeah. So now, if this is the case, then how exactly we are formulating we are analyzing the system and we are coming up with an algorithm and how we are validating that system in the hardware, the control algorithms and all, we look at. Yeah, so this system can be, you see, mathematically I can write like this, I can draw like this. How do you draw that? You see. So this inverter is a generating high frequency voltage. I can write like a simple AC voltage source, correct? So that only what we are writing here. High frequency AC voltage source. Inverter is not there, mathematical representation. And you look at here, this one. So how do you represent this this coils actually, transmit array and receiver? This is like a transformer model. With the independent sources I can write it down. So this itself, the channel itself I can represent as a dependent source, you see. This is the one. Coil with a dependent source. Why dependent sources, you see? So you know coupled coils are there. Coupled coils are there. Current flowing through the coil. I1 is the current flowing to the primary. I1 set up the magnetic field. Correct? In the coil 1. That magnetic field will link the secondary coil. Secondary, there is a induced EMF. The load is connected, there is a flow of current. Correct? The secondary coil I2. I2 again set up the magnetic field that also induces the voltage in the primary coil. So what happens is, there is a coupling between the primary and secondary that is represented through this one. This is the dependent sources. See, ITA is the current flowing through this one. This current induces the voltage here. That is the source represented by this one. Okay? So this current, okay, IRX1, this current induces the voltage here. That is represented by this source. Okay? This is a simple magnetic model of the transformer we are representing. So like that, every channel 1, channel 2 and channel 3 and so on we are representing and connecting the equivalent resistances. If you are analyzing this model, what I am trying to show from this analysis is that, so some of the takeaway points related to the charges, I will make some conclusions. That's only what I am trying here. So through this analysis, so this RCA is look at equivalent series resistance. We are keeping here, this is a battery, right? Battery equivalent resistance. So that when we are representing on the AC side, we will write in this fashion. Using the standard way. And as I told you, 79 to 90 kilohertz is the static. And the resonating conditions. Resonating conditions means this coil and this compensation network are resonating conditions. That is W naught. Some of the equations we are writing for the cells compensation and I am keeping here. Okay, but finally what I am trying to say is, you see, I can write this network as like this. This whole network as like this. How? You see, this is a VIN, correct? This is a VIN. Okay? JX minus JX plus JX and ZT. So overall network I am representing in the form of T network. Some T network which is having a reactance as JX minus JX. What is the JX and all? I can do some network analysis and I will come to that configuration. Right? So now from this analysis, what I am trying to see is the input impedance seen by this network. Network means input impedance seen by inverter, Zin. Zin equal to is a function of the resonating frequency. What is omega naught here? Omega naught is the frequency of your inverter. Inverter is operating at 85 kHz, that is omega naught. Okay? That impedance seen by this network is a function of omega naught and this inductance LFP, okay, and ZTA, transmitter array impedance. What is the transmitter array impedance? So this is the one, right? So now, if you are computing the ITA, current flowing, current, this current. ITA is a function of input voltage, this voltage, by J omega L. And you see, ITA, this is one of the important expression. ITA is a function of input voltage and frequency and L of P. Surprisingly, this ITA is not a function of secondary currents. Did you find? Did you get the point? ITA is not a function of secondary currents. What is happening, especially in the transformer? So you have load current, equivalent current you are drawing from the primary current, correct? So, but you see, IT is not a function of secondary current here. This current is not a function of this one, decoupling. Okay. So, what we are trying to say is only IT is a function of input voltage and switching frequency and this component value. Okay. Right. So, this is one of the important points for this work actually. Yeah, so further we are analyzing finally efficiency also we can see from this system. I think through network analysis you can carry out the efficiency also. I think you can do it. It's not a big task, especially network thing. And if you see from this analysis, efficiency analysis and all, after performing, what is the detail is this quotient of coupling between these two coils, if you could draw as a function of load, as a function of load. So this load is load is the quotient of coupling. Load, so it is decreasing like this. Okay. That means you see, when you are charging the battery, what is happening? Voltage of the battery is rising. And current pumping into the battery, we are using a constant current charging, voltage is increasing, V by I, terminals across the battery, you look at V by I, V is increasing, current is constant, resistance is also changing. Resistance seen by the battery is also changing, correct? That resistance only what we are talking about here, okay? And it is changing how the quotient of coupling is changing and all. I think some optimal analysis are get over here. Yeah. And one another point is, I think I will just give you the idea. So one another idea is you see. So this converter, right? This is operating at 85 kHz, right? When it is operating at 85 kHz, one of the other challenging issues, suppose we are tackling about 10 kilowatt hour with 85 kHz, correct? So 100 kHz you require 10 microsecond time. Within 10 microsecond time, switch has to turn down, turn on. Okay? Switching losses you see. Turn on, turn off, switching losses are there means your converter efficiency will degrade and also thermal aspects also will degrade, temperature also, correct? So in order to tackle that switching losses, otherwise hard switching points, so we also see whether the converter is operating under soft switching condition or not. Zero voltage switching is happening in the converter or not. If it is happening zero voltage switching, then what happens? There is no switching losses in the converter. Correct? You know, switching, zero voltage switching means what? So when suppose you see the short switching, especially when the current and the voltage of the switch is going to zero, then only current is rising. Both may not rise simultaneously. Then there is a hard switching, then efficiency of your system is good. Especially when you are targeting the high frequency converters. One of the way is whether our converter is operating under soft switching conditions or not. That that analysis also you need to perform. If it is not operating, what are the conditions you need to fulfill in order to operate that system in the source switching conditions? That is the one of the very important aspects in the power electronic converter. Charges also, of course, it is applicable. I mean, charges contains all power electronic systems. So that analysis, ZVS, zero voltage switching analysis for this converter also we carried out in order to tackle these losses. So that's why this analysis especially. So we found some boundaries. If you are operating the converter in that boundaries, then we will get a good efficiency. That is the takeaway points from this analysis. And next one is maybe here. As decoupling of the, suppose series connected coils are there, right? One vehicle is coming, first one vehicle charging, next another vehicle in the second channel is also there. During such conditions, what happens? There should not be any coupling between these two channels. We need to decouple. In order to validate that point, then we made some sort of studies here. Through that studies, what we concluded is, even though you are adding, you see, up to here, only one vehicle is there. After that, we are adding another vehicle. Then there is no change in the ITA. It remains constant. There is no coupling. That is only what we are trying to say from here. Yeah. So this is of course a closed loop operation. So how exactly we are changing from, as I told you, as a charger. Current control mode to voltage constant current, constant CC mode to CV mode, constant current to constant voltage control. That mode how we are changing, how exactly we are controlling the converter. That part also we did in the laboratory. And same thing, I think we validated through some sort of experimental setup. Level 1 charger, 3.7 kilowatt. So you see, these are the systems. I think I showed you, right? I told you this wireless coils, liquid, right? So this is that coil you see. These are the liquid. Secondary coil, primary coil is here. The space between the primary and secondary you get. Here we managed about 150 mm. Okay, 150 mm in the laboratory. And these are the compensation capacitors, small capacitors. Okay, this is one channel, this is second channel. Two channels we connected to validate this idea. And we apply, you see here the different, this is the power electronic converter, high power electronic converter to silicon carbide switches. And these are the LCL compensation. I told you not, this LCL compensation we are using here, right? Now, this is inverter, LCL compensation, and primary secondary coils, divergence rectifier and so on, right? This LCL compensation, we wound the air cooled inductors, you see. These are the LCL. Two inductors and one C. And you see, and this is one channel, this is the second channel, and the corresponding coils and corresponding inductors, secondary side inductors. And this is the direct rectifier and connecting to the load. Instead of connecting a battery, we connect the variable resistor. Variable resistor is mimicking the battery characteristics. As I told you, if you are charging the battery, voltage is rising with a constant current. Resistance across the resistance seen by terminals of the battery also vary. Same thing we are mimicking here. So through this tube. So and then of course these are like DSOs. Okay, we have a DSP here. Okay, we are using a DSP to fire the silicon carbide devices. Yeah. So we are applying about 250 volts into the inverter, DC voltage. Okay. And switching frequency is 87 kHz, and other parameters are given. With this setup we made about we tested about 3.7 kilowatt and this 5 kilowatt setup. Easily. And these are some of the hardware results. Okay. So see this yellow color one. Okay. Is the 85 kHz output voltage from the inverter. Okay. But you see this current, this green color. What is this voltage actually? This voltage is nothing but output of your inverter. Correct? What is this current? This current is this current. This is the one input current. Input current means before LCL filter, inverter output current. But inverter output voltage is the square wave, but the current is not a square wave. Why it is not square wave actually? Why means inverter is not seeing resistive load. It is seeing some sort of inductive nature. Correct? But when inductive nature your inverter sees high frequency square wave is passing through some RL circuit, then what happens actually? So all the harmonics present in the square wave is gone. So it is shaped, the shape is looking like this. Correct? Okay. If pure inductor, pure resistor is there, inverter is connected with a pure resistor, correct, right? Then we will get only square wave is the current, but it's not square wave is not a current. Inductor is saying some other way. We are connecting so many channels and all, and also we are operating the converter under inductive region in order to get the ZBS operation. That is the reason why we are getting such type of connection. The sine wave, but see, you see, ITA current. ITA means after LCC filter. You have LCC here. Here, this current. I am showing this current earlier, and this is the current now you see after LCC. So this filtering network is eliminating all the components of the. It is act like a filter, and we will see only sinusoid current here. But sinusoid current one can see here. It's pure sine, you see, 85 kilohertz, right? So ITA, right? So then this is the diode which input, and these two are the primary side voltage and current, the secondary side diode which voltage and current. Okay, right? We are multiplying them, we will see the power actually. Okay, right? So this is ITA. So first case. Second case, look at this case. What we did is we are changing the battery voltage. You see, battery voltage is higher here. Here battery voltage is low. Why means we are trying to mimic the SOC of battery. Battery voltage are down. Under such conditions, how we will see. So this, okay, one with a one channel with a one vehicle with a different battery voltage, another vehicle with a different battery voltage, second channel. That is the idea. But see, primary current remains same. And the next you see input voltage, and input voltage is also varying, and how charger performance and all that is verified here. Yeah, so I think we changed the current also, of course. See, different currents we changed, and we saw how it is acting, and different case studies we made here. And finally, ZBS and ZBS operation, zero voltage switching also we verified here. The switches are going through soft switching or not, waveforms are shown. And efficiency, look at 4 kilowatts, we tested at 4 kilowatt, we recorded about 95% of efficiency on this converter, for charger, 4 kilowatt, level 1 charger, 150 mm distance. And maybe load resistance versus output power, channel wise, one channel, we are doing another channel that is making. See, one channel there is changes, another channel is constant. Decoupling and all verified through experimental studies here. Yeah, so some advantages and compared to the conventional charges and all we highlighted in this table. Yeah, so that's all about this system. This is one of the work carried out by one of the research scholars. I think maybe I don't know how much really you understood, but the thing is the key idea we understood that is fine. This guy spent about 4.5 years and he did this work. It's not so right. So it's not so easy to carry out all this analysis and all. Of course, he reported other works also along with that. So with this, maybe I will give a 2 or 3 minutes of break. Time is there? Or I have small. 15 minutes. 15 minutes. Just in 2 minutes break. 15 minutes.
Okay, session will end in 10 minutes. After the session will be arranged beside 10 minutes cover. Okay, we will felicitate after that we will end of the session.
transfer. Just I will give you an idea. What is DWT and all? These are all we discussed. Yeah. So this is the idea. Okay. I think we have this black color one is the road, correct? And you have different transmitter coils. Transmitter 1, 2, 3, 4, 5 and so on. So there are two types of technologies, long tracks and short tracks. Okay, there is a short track technology. Okay. So here how we are exciting these transmitter coils which are buried under the road. That's one of the idea. You see, you have an inverter, as I told you, high frequency inverter. And high frequency inverter is connected to the common DC bus. Okay. And also, same inverter is interfaced with the renewable energy. We are integrating the renewable energy through that inverter as well. So this charger, what we are calling here is a renewable assisted GWP system. Right? So this inverter is doing a multi-functions here. It is harvesting the maximum power from the PV panels, and also is converting the, and also it is exciting the it is exciting the transmitter coils. These are the two functions it is doing. Right. So how it is doing? There are two variables inside that control. One variable is a phase shift, another variable is a duty cycle. These are the two variables. The two variables you can control maximum power point as well as excitation of high frequency voltages. Right? Yeah. So I think this inverter is fed by exciting these two coils. This inverter is exciting these two coils and so on. Multiple coils can be excited by a single inverter. There is a concept. This concept only people are using in the research currently. And vehicle, of course, you have vehicle front side and back side. You have a bus, okay, 1.5 meters front side and back side, receiver coils are setting. And the receiver coils you see are connected parallel to this battery pack which is sitting on the vehicle. So vehicle is moving at a speed of 60 km per hour, 70 km per hour. We are charging the batteries in the vehicle. That is the idea of DWP. But this concept is verified at the laboratory level, as I told you already. We also made some sort of attempts in our laboratories, as your friend is also asking. That I wanted to highlight, not into the deep, I just show. Okay? Yeah, so there are some literature, I don't want to show all these things you see. The main idea is this, as I told you, PV power and excitation of these coils is done by this inverter. Inverter 1, inverter 2, inverter 3. And the output side you see, the vehicle side, both the power electronic converters are connected parallel and feeding to the battery, and this is the high frequency link. So this is the one what we are calling these parts. I think that this setup what we did is we made some sort of operating modes and we explained control of the device and some simulation results we captured, and I will go directly to this. Yeah. So one transmitter coil and this one to look at coil designs. Yeah. So I think you are asking about the lead wire, right? This is the one what we are using. This is the lead wire. Circular coils what we use here. You see, this is the lead wire. This is something different from our conventional wires. So what we have here is, so inside this wire, white color is the white color nylon insulating wire what we have. Breakdown strength is up to 1.5 kilo, and we have about 1000 strands inside that. Each strand is 0.01 mm. Imagine 0.00 mm, very small actually. In order to tag that skin depth we are using especially. So yeah, so this design that we made with the help of some calculations, usually LCR methods to vary very well. And compensation capacitors also made some designs, and after that we attempted to test them with the setup. You see, These are coils and this is the inverter and the compensators and all. And we took some waveforms here. Here you see. These are the coils, right? So this is the first coil, transmitter coil, this is the second transmitter coil. Correct? So this is the receiver coil. We are trying to move this receiver coil. Actually, in this figure I didn't show how we are moving. We kept some trolley. So the trolley secondary coil is sitting on the trolley and we are moving transmitter coil. So and this transmitter coils, maybe we made some distance here and sometimes I think when we are changing this distance, what is happening, how exactly magnetic neutrality and so many points are here, so many challenges are there. The points which we are trying to address through this ANR project. Currently, this is only our project, which is worth of about 2 crore. And studies, I think we made that only one alignment and one receiver is exactly aligned with the transmitter 1, transmitter 2 and in between the positions we saw and we captured that results when we are moving it the trolley, how exactly you are getting you see. So see when your receiver is at the middle, you are not getting anything, 0. When your receiver is any one of the transmitter, you see you are getting this. When it is moving, you are getting it. But this is not a good practice, right? Power fluctuations are there at the output. Battery is not charging during that time. This is one of the drawback. This is what the literature is reporting, correct? So that is the reason why what people are making is that they are going with a changing the designing of the coils. The structures may not support the power fluctuations and magnetic neutralities there. So people are using some structures called as DD coils. DD, shaped DD coils. Through DD coils, this type of power fluctuations may not happen in the building systems. But we are working, maybe we achieved up to some extent, but efficiency we are working right now. Since it is in the research phase, I didn't highlighted these points by which we need to go for the publications and some other things. So it may go to the public platform, that is the only idea you want to share on these points. Okay, but the idea is this. Yeah, so with that maybe I will stop. Thank you for your patience. Even heterogeneous people are there, maybe I don't know whether I can convey or not. So I'm happy to see the other results. Thank you. Thank you for being here.
Now, from participants, any questions?
Yeah. If you have any questions, I'm happy to address. Otherwise, maybe some of you are doing some research. You can connect with me, no problem. I can also throw my email ID. If you are doing research in this email domain, I can help you.
Thank you, sir. It's time for thanking and felicitation of the resource person. On behalf of the organizing committee, I extend our sincere gratitude to Dr. SRKREC for his insightful and informative session on electric vehicle charging technologies. So this session has given us new knowledge and ignite our research minds to expertise new ideas in field of the EV. So, your valuable insights and expertise have greatly enriched our understanding of the latest developments and challenges in EV charging technologies. We truly appreciate your time and efforts in sharing your knowledge with us. As a token of our respect and gratitude, I request our Pedagogy Department Professor PHR to kindly felicitate Dr. SRKREC. by also a host, a coordinator and co-coordinator of the FDP to kindly join as an express our sincere appreciation with a warm round of applause. Thank you so much.
All the participants can join with us. We will have a photo session.
Is it okay?
1 minute, sir.